Okay, so last time we were talking about line integrals, right? And then I modify the term slightly. I talk about scalar line integrals for reasons that will really not become entirely clear until we talk about a completely different kind of line integral today, actually. That is not the same as a scalar line integral. Okay, anyway, so scalar line integrals is what we talked about previously, and now we're gonna do a pretty expected next step. Let's talk about surface integrals, right? If you can do an integral over a curve, right? Chop it up, add it up on a curve. Doesn't it seem reasonable that you might want to chop it up, add it up on a surface, right? So here's a picture, for example, of the kind of surface that we might want to. Maybe I want to compute the amount of mass that there is on this surface, and I know density is a function of position, right? That'd be pretty plausible. Or maybe there's this is a side of a hill, or so maybe not this part here, but this is a side of a hill, and there's some sort of a plant that's growing, but how dense the plant is depends on altitude. This is very physical. Right? It's very real. So you have a non-constant density that depends not on sort of where are you within the parameterization, but where are you physically in space. Right? You want to know how many plants are on that hill. Well, you need to do a chop it up, add it up. And sure, the details are a little bit different. Here, we're going to be chopping into little pieces of area by making multiple kinds of slices in one direction, but then also in another direction. Right? But it still remains the case. I'm going to take a whole large thing. I'm going to chop it up into a bunch of smaller things, right? And I'm going to solve the problem in question on each smaller thing. How many plants are growing on this one little tiny little patch of the hill? Well, I know what the altitude is there. And I know how big that little piece of the side of the hill is. And plant density, plants per unit area times the amount of area tells me how many plants there are there, and I just want to add up those numbers for all the pieces. So, it's still same morally, same general idea. So, we're going to make this definition here on each little piece. If there is some function, whatever that might be, appropriate to the application. Maybe it's plant density. Maybe it's mass density. Who knows? Whatever. Some appropriate to the application, and then multiply by size. That didn't take right. Here we go. Multiply by size of that little piece of area. This little calculation should tell me, depending on the application, how much of the quantity in question I have on each piece. I then want to add that up over all of the pieces. So again, a very familiar concept. Let's talk about notation. Hopefully no surprise. If I'm using delta S to represent the surface area of a little piece of the surface, pretty plausible that I would denote, shorthand that as ds, right? Following our pattern. The integrand, again, we need to stick that in there. Got to know what that integrand is, appropriate to the application. And then we're doing a limit of a sum. We're going to denote that with integral symbols. And again, not all books do this, but because we're adding up over two indices, right? This is a two-dimensional piece of surface, two integral symbols. Okay. A lot of books do this, some books don't. Okay. And finally, as usual, in order for this to make any sense, we have to know what that domain is. You got to tell me what exactly is your surface. And as we have for many other kinds of integrals, we'll indicate what the domain is with a subscript. Okay, so when you see this notation, your thought should be, look, chop it up, add it up. I'm not chop up, add it up on an interval or a two-dimensional region in the plane or a solid in space. I'm doing a chop it up, add it up over a surface that's sitting inside of space. All right. So, easy, quick example. And by the way, notice nowhere Have I yet given any discussion of how to compute these things? Right now we're focusing on what is the nature of the Riemann sum, and how can we see that such a Riemann sum would allow for certain kinds of applications. Okay, so the computations will come soon, in fact right after this example. But suppose you want to compute the mass of this curved sheet of metal, right? Well, on each little piece, mass per unit area times area tells me the amount of mass in that piece. And then I want to add up over the whole surface. And that's what this says right here. On each piece, the amount of mass is, I need to know mass per unit area, we're calling that our density here. Multiply by the area, that should give me the amount of mass. Add up over all the pieces. And that should give me the total mass. How are we doing? Is everybody on board? Familiar? Right? You might even say expected. It's the same general structure. Okay, so how do we compute these things? Well, yeah, that's a question, isn't it? Here's the general strategy for computation. We have another domain that we don't like, right? We've seen a couple of examples already. If you have a domain that you don't like, if you can view it as an image of a domain that you do like, right? Then the idea is the original integral, being as it is an image, everything that is written over here can be rewritten. You can just plug in the parameterization, basically, rewritten in terms of an integral over here. This is our general pullback strategy. This was how we were viewing change of variables. This is how we viewed the computation of scalar line integrals. Parameterization was the function through which we pulled back. So here we are again, and can I view some ugly, nasty surface here? Can I view that as being an image of something? Well, yeah. And by the way, again, parameterization. It's just that now we're talking about parameterizing a surface instead of parameterizing a curve. Again, we have methods for this. Right? So this goes back to chapter 2, I guess it was. And those parameterizations of the surface will allow you an opportunity to do a pullback. Okay. All right. So what we've got to do, just like we did in our previous pullback strategies, we need to recognize that when I do a slicing in my pullback domain, right, the amount of area in each piece here, not the same as the amount of area in the image piece over here, right? That amount of area is clearly different. Oh, whoops! I forgot to change the color. There we go. Clearly different. Because this parameterization, I mean, it's not just going to gently pick up my rectangle and place it into space. It's going to bend it around and stretch it and contort it and all sorts of rough things that's going to happen, right? So I need to figure out what is the factor by which areas get stretched here. This area is what times that area? Just like we did with change of variables. There's a temptation to say, hey, why don't we just use the old change of variables formula, right? I mean, didn't we already do this? Change of variables output, we got a little parallelogram here. Want to know what is the proportion by which that is, its area is a multiple of this, and we computed these edge vectors. It was partial derivatives times du and dv. And how do you compute the area of a parallelogram? Well, it's the determinant of the little matrix, and you do a little algebra and Jacobian determinant. Aren't we done? Tempting, right? The big difference is really I'm going to say little difference, and that is this parallelogram is not in the plane. Right, the formula that we used way back when for, if you have a parallelogram, what is that resulting area of that parallelogram? That formula, take the columns, take the determinant of the resulting matrix, take the absolute value. That formula assumed you had a parallelogram in 2 dimensions. Critically, here we don't. That's kind of the point. Everything else is the same. So this calculation, I mean, there's going to be a lot of familiar stuff here. I'm going to understand this thing here by its edge vectors. I'm going to look at that little vector, E1 du, and I'm going to use the derivative transformation to find its image. And then I'm going to look at this edge vector here, E2 dv, and I'm going to use the derivative transformation to find its image. I mean, that's the same thing we did previously. And then awkwardly, again, we have to recognize these are vectors in 3 space now, not vectors in 2 space. Yeah. Okay. Right. So here's sort of a picture of, blown up large, right? Here's our piece of surface, of which we're trying to compute, an area. Those edge vectors that I just drew, do like this. Those edge vectors are, tangent vectors over here at this base point. Here's the second one. Old news, we've already done the calculation of what those edge vectors formulas are. It's derivative transformation times actually let me go back to where I have this calculation written out. Derivative transformation times are applied to those input vectors. Here's the input vectors, E1 du, E2 dv. Apply the derivative transformation, and there's your output vectors. Now, notice, in these calculations, the same little algebraic dance happens. In both cases, we observe that these differentials factor out. We observe that the remaining derivative transformation computations that we're doing here, derivative transformation, are both applied to standard basis vectors. Therefore, give us directional derivatives where our velocities are standard basis vectors. In other words, it gives us partial derivatives. So all that's familiar. It's the same story that we saw back in change of variables. Okay, so again, with the familiar formulas, there's the first edge vector, there's the second edge vector. Okay, well, the new story that we have is, again, I'm trying to find the area of this parallelogram, the idea being that this parallelogram approximates our little piece of surface, and so if I can compute that area, then I'm good. Here's the one place where everything changes, and that is that, well, again, this parallelogram is not in 2 dimensions, this parallelogram is in 3 dimensions, and even though we can't use that same old formula, we can use a different old formula. We have a different old formula for how to find the area of a parallelogram in space, and it's the magnitude of the cross product. So here's that calculation. First edge vector, second edge vector. The area is the magnitude of the cross product. Hope everybody remembers that formula from chapter 1 long ago. Not that long ago, of course. Okay, so again, going forward, we're going to do some familiar tricks again. The du and the dv factor out. That's convenience of how cross products work. It's also convenient in how magnitudes work. Those factor right out. And look, now I've got exactly what I wanted. I've got that output area viewed as some multiple of the input area. Right, looking at my parameterization, du dv is the area of that little input rectangle in the pullback domain. ds is the resulting image area in the parameterized surface. And we have ourselves a stretching factor. Right, that stretching factor is that thing right there. It's the magnitude of xu cross xv. Everybody on board? I'd say it's change of variables all over again, with this one twist that we have to use a slightly different formula to compute the area of the parallelogram. Other than that, it's change of variables. Okay. All right, now for convenience, it's going to turn out not only here but in other situations that this vector here, this vector whose magnitude is our stretching factor, that vector is going to end up being really useful in other places, which we'll see tomorrow, actually. Anyway, so for convenience purposes, I'm going to give this a name, and this is reasonably standard. Now we're going to call this capital N. So henceforth, I'm going to use capital N to represent exactly that. It is the cross product of the partials of a parametrized surface. All right, so we've got it all pretty much done at this point, and so therefore here is our result. How to compute? If you want to compute a scalar surface integral, if you want to do a chop it up, add it up on a surface. In other words, if on each little piece of the surface you're going to multiply some integrand appropriate to the application times the size of that little piece of surface, and if you're going to add up over the entire surface, the usual, right? Then with our stretching factor identified, ds turns into this. Again, here's our stretching factor. Everything else is just a matter of plugging in. F is a function of x. X is now a function of our parameters, u and v. So said differently, plug in the parameterization. And we just pulled back our integral. Everybody okay? Everybody happy? Okay. Alrighty. Okay. So let's see an example. We have already talked about the sort of the phase one part of this question here. Suppose you have a metal sheet so it's a two-dimensional metal sheet, but again, it's embedded in space. Specifically, we're talking about a surface, and here's more specifically, this surface is a graph of this function here. More specifically, the part of that graph that is sitting over the unit disk in the xy plane. So what we have here is our surface is shaped like a bowl. I think about the graph of this function, how that sits over the unit disk. We're looking at this bowl. We want to compute the mass on that in that bowl, not in the bowl, but making up the bowl. And density, again, not constant. So it's not like I can just compute the area and multiply by some fixed constant density. The density varies pretty dramatically there. Right? Okay. So how do I compute the mass? Well, we've already talked about, again, what you might call the phase one part of this problem. Total mass is the sum of the little pieces of mass that you get when you slice this surface up. On each little piece, mass is density times area. So phase one, turning the application into a surface integral, familiar. Okay, phase two, how do I compute this thing, or how do I rewrite this as an iterated integral? And that's where we're going to use this result up here. We need to parameterize our surface. We need it to be parameterized. And I need to know what this parameterizing function is. Let me just remind you why we need that parameterizing function. We need to know this parameterizing function because that is what we are pulling back through. That is the function for which we need to know the stretching factor. Right? That is also the function that we will be plugging in. If we want to rewrite, x, y, and z, if I want to rewrite those in terms of u's and v's, which I have to do, I will be plugging in this function, right? So everything in this kind of a calculation boils down to what is your parameterization. So it's got to be step one, parameterize your surface. Okay. So we are looking at a graph. So you'll notice I'm using the graph parameterization. You'll further notice that per that strategy, I make the first two coordinates the input parameters, and then I plug the input parameters in to get what the third coordinate should be. It's straight out of Chapter 2. This is how to graph parameterize a surface. It's my favorite trick for parameterizing surfaces. And when you possibly can, this is a fantastic choice. It's not the only choice. There are variations, of course. All right. Okay. Everybody on board so far? Okay. Oh, let's talk about what the domain is for this parameterization. What's my pullback domain? Reminder, the whole point to a parameterization is so that I can pull back my integral to a new domain. We need to know what is that new domain. Well, with a graph parameterization, conveniently, the whole idea is that x is u and y is v. So if I want to know, using a graph parameterization, hey, what's the range of values of u and v? Well, u and v are x and y. So look back to your original surface and ask, what is the range of values of x and y? That's your range of values for u and v. That in mind, notice we are looking at the part of the graph that is sitting over the unit disk in the xy plane. And so the pullback domain is the unit disk in the UV plane. Because x and y are u and v. Let me hit the pause button on this. Anybody have a question about that? Yes?
Does that mean that at the end, the bounds on your integral will be like 1 and -1, and then like the formula for the unit disk?
Yeah, pretty much, yeah. So depending on whether you do du, dv, or dv, du, yeah, the outer bounds are going to be -1 to 1, and then the inner bounds, let's say you're doing dv on the inside, those v inner bounds will be plus and minus square root of 1 minus u squared. Yep, exactly. Everybody on board with? Okay. Cool. Okay, so we've got our parameterization, and now it's somewhat plug and chug at this point. The formula tells us what to do with our parameterization. Once you have your parameterization, we need to compute the magnitude of capital N, that being, of course, xu cross xv. So we're going to have to take some derivatives, take a cross product, take a magnitude. It's a little tedious. That's what the formula tells us. Right? We, of course, also will be plugging in for x, the x vector. We will be plugging in, using the parameterization, what those x, y, and z coordinates are in terms of u and v, again, from the parameterization. So, little reminder here, this is x, that's y, and that's z. So there's how you plug in for x, y, and z. Okay, we'll get back to that in a minute. Okay, so first let's compute our stretching factor. Here's that calculation. General formula. All right, we're going to need to compute the u partial of our parameterization, and we're going to need to compute the v partial of our parameterization. There's our parameterization. I'm just copying from the previous page. These partial derivatives. That's pretty straight up partial derivative there. Right? Likewise, there. Now you got to compute a cross product. Okay, so again, flashback to chapter 1. Just a reminder. I mean, I've commented on this before, but this class has got a very vertical kind of structure to it, in the sense that the stuff later in the course relies on, is built upon stuff we've done early in the course. So notice we're going to need cross products, right? So make sure that you remember how to compute cross products for these calculations, how to interpret cross products as giving you areas of parallelograms per the argument we made here. Right? So, okay. All right. So that cross product works out to be this. Then we have to compute a magnitude. There's a lot of annoying details in these calculations, but that magnitude, it's a matter of writing it down, is this. So there is our stretching factor. You'll notice that stretching factor pops up here as we rewrite ds. That's just me rewriting ds right there. Huh? Okay. Plugging in the parameterization. So again, don't forget that x pulling back is now a function of u and v. Here's what that function was. There is our parameterization. Again, copied from the previous page. That tells you x, y, and z as functions of u and v. And that's therefore what you plug into your density function. By the way, what was our density function? Let's see here. Yeah, here it is. Our density function is z squared. So here, this density, z squared, don't forget z is u squared plus v squared. So, there you go. Okay. How we doing? Questions? Everybody happy? And this is very kind of, the argument that we're making here, it follows a pattern from previous arguments we've made, and the computations are plug and chug. So there is that. Okay, I'm going to go ahead and bleed you all that everybody's happy. Okay.
Wait, so you said
Yep.
the bounds would be -1, and
Yeah, well, that's right. So that's right. So I didn't write that down here, but if you were to take this now, notice we have a double integral in the UV plane. Right? If you were to actually explicitly write this as an iterated integral, then yeah, the bounds would be v would go from -1 to 1.
u would be plus or minus square root.
Yeah, that's right. If you do it in rectangular coordinates. Now, let's take a pause there. Just because I have this written in terms of u and v doesn't mean I'm not stuck with that, right? We are still, in fact, allowed to compute this integral here any way we want. And I have a strong preference for how to compute this integral. Let's think about how this would break down if, per your question, these bounds here would be v goes from -1 to 1, u goes from negative square root of 1 minus v squared to positive square root of 1 minus v squared. Right? And, man, that looks rough, doesn't it? Especially keeping in mind that after you've done your du integral, these square roots then are going to get plugged in, and not only will you be dealing with the after effects of anti-differentiating this, these square roots will then show up as well. So you're going to have an ugly v integral here. So how about we do this in polar coordinates? The nice thing about doing this in polar coordinates, let's think it through. The disk, that's a unit disk, has constant bounds in polar coordinates, right? Theta goes from 0 to 2 pi. R goes from 0 to 1. No square roots. Furthermore, this kind of ugly term here, u squared plus v squared, quantity squared, becomes r to the 4th in polar coordinates. It becomes one term, not arguably 3 terms when you square it. Likewise, this will simplify at least a little bit. So this is going to be a much nicer integral in polar coordinates, both because the integrand simplifies, but arguably more importantly, because the domain is simpler to deal with in polar coordinates. Okay, pause for questions. Yeah.
So we just allowed to choose which type of coordinates we want to
Yeah, these are tools in your toolbox, and you may use them as needed. Yeah, unless specifically indicated otherwise. I mean, I have written test questions in the past. You all can see in my old where I say, I specifically want you to do this in rectangular coordinates because I want to either I'm doing you a favor, right, of saving you let's try this in cylindrical and it turns out to be bad, or I want to see how, I want to test specifically your knowledge of how to slice in rectangular coordinates. So yeah, but other than that, if you just, in life, if you find yourself with an integral, you have various tools and you may use them. You have my permission to use all of your tools as you see fit. Yeah. Anybody else? It's a great question. Yeah, here's another thing. So along the same lines of your question, there's a temptation to look at a problem and think, oh, this is a scalar surface integrals problem. And therefore, somehow it is, by exclusion, not a polar coordinates problem. Right? But it just doesn't work out that way. And I remind you, back in Calc 2, sometimes you do a substitution, and the result of having done a substitution is that you get an integral that you can break down with integration by parts. Right? So sometimes you have to apply multiple methods, and so likewise here. Yeah. Okay. Yeah. So this next example, I'm not going to spend any class time on, but I think this makes for a good read. It's kind of fun. I think I wrote this after I went to an aquarium. And side note, they have a very nice aquarium here over on in just beyond Atlantic Beach. Anyway, not interested in that sort of thing. But the idea here is that the water is here, and you've got a bunch of fish, floating around in there, and maybe a shark or something, right? And they have a hallway down here where you can walk around, and then there's a little bubble, and you can stick your head up inside of the bubble, right? And then as you look, it's like you're sort of in there with the fish. This is kind of neat. So anyway, they've got a million of these kind of things in different places. But the question that this question addresses is, okay, well, there's going to be tremendous amounts of forces on this dome, right? And how can you compute the total amount of force that's on that dome? Well, it's what we call a hydrostatic pressure situation, and so depending on how deep you are, when you are deeper, there's more pressure, and pressure times area gives you force. So per unit area, there's a lot of force down here. Per unit area, there's less force there because it's not as deep, right? So grand total, how would you compute the sum of all these forces? Just for, if only for a sort of amusement. But anyway, this question will walk you through that, and it's a nice exercise. We use a spherical graph parameterization. I think is kind of cool, right? So there's a bunch of good little aspects of this example. I want to encourage you all to read through it, and yeah. Okay. So we're going to move on to the next section then, vector fields. I want to talk first about why we're talking about vector fields. Every integral that we've seen so far has been an integral where the integrand is a scalar function. Real valued. Just a number. Right? If you think about triple integrals, when we did a triple integral of density, that's a scalar. It's a number, right? Concentration, it's stuff per unit size, kind of like a density. Again, it's a number, right? Okay, that's no longer going to be the case for the next kind of integral, next couple of kinds of integrals that we're going to define. So we need to talk about what are these new integrands that we're going to see. We need to have previous experience with the objects that will be our new integrands. So that we can, when we get to defining integrals of them, we'll be ready. Okay. And there's another thing. This has been the case for every integral that we've seen so far. That, you do an integral, you have an integrand. That integrand is computed based on location. If you want to know the density here, this point on our rod area, whatever, the density at that point, the thing that you multiply by your scalar differential, that thing, it depends only on where that piece is, just where. That is also not going to be the case in the next kinds of integrals. It's going to depend on how that piece of surface is oriented. That's real hard to see this coming right now. But there are some significant oddities that we have never yet experienced that are going to rear their ugly heads with our next kinds of integrals. So anyway, we need to talk about these things. Specifically what's going to happen is our integrands are going to be vectors instead of scalars. Okay. So let's talk about the first kind of. We're going to define something called a vector field. There are several physical examples that y'all will hopefully be able to relate to at least a little bit. The first one I'm going to talk about is something called a force field. It's not like in the sci-fi, right? It's a different thing, completely different. The idea is this is a vector field where the vector field represents forces. Okay, so let's talk about gravity. Here's our picture that I want to draw. Here's our, let's say, Earth, right, our little blue marble. And I think y'all are aware of this, but gravity is, we experience it on the surface of the Earth as being kind of constant, right? You go to the top of a tall building, you feel the same, right? And that's mostly a function of the fact that we don't ever get very far away from exactly the same distance to the center of the Earth. We're pretty much always, whatever that is, 4,000 miles or something away from the center of the Earth. Okay. But if you get out into space, when you're some distance away, there is a corresponding amount of force of gravity of the planet pulling you toward it. But then when you are a significantly different distance away, there is a significantly different gravitational force. I mean, everybody knew that, right? I hope. And y'all have probably also seen a formula for this. It's the inverse square rule for gravitational attraction. So, yeah, sure. So the inverse square rule, they tell you for me, it was in the 9th grade physical science class, they told me that rule. It's more complicated than that in the sense that, keep in mind, forces are not just scalars. Forces are vectors. Forces have directions. At this point, the force isn't just a quantity. It's a quantity in that direction, right? So what we have then is a pretty complicated scenario. If I want to describe the gravity created by the Earth, at every point there is a corresponding force vector. So at that point we have that vector, and at this point we have this vector. Though coincidentally those have the same magnitudes, but they're different vectors. Because they're in different locations, those forces are pointing different directions. Okay. Likewise, at that point, we have a different direction and a different magnitude of force vector. Okay, so altogether, if you wanted to represent, what is this, gravity, Earth is creating it's acting in different ways at different places. How can I draw a picture of what is this thing? What is this gravitational thing that the Earth creates that, wherever you happen to be, creates forces? And a pretty good way to represent that is with a picture like this. Just draw, a representative sample of points, and then their corresponding, what is the force vector? So this is our first picture that I'm going to show you of a vector field. This is a vector field because at every point there is an associated vector. Ultimately, that's going to be what a vector field is. For every point, there's a corresponding vector. In this case, this is what we call a gravitational field. I'm sure y'all have heard that term bandied about in a lot of science fiction movies as well. In fact, probably correctly. This is a gravitational field. All gravitational field means is it's a vector field, right? Which at every point, the associated vector is the vector representing gravitational force. Okay. All right. Okay. Yeah. All right. So now that's just one example. And by the way, I mean, there's gravitational forces. You could draw a similar picture for charged particles and their corresponding electric fields. If y'all haven't had an E&M course, no problem. I mean, we're going to do a little bit of stuff with E&M here, but nothing too terribly. I'm not going to assume very much. But right now, here's what I'd like you to know about charged particles and electricity. If you have two charged particles, there is a force between those two charged particles. It's not unlike a gravitational force. It's just a different thing. It's an electric force. And side note, if the two charged particles have the same sign of charge, then it's a repelling force. It's weird. If they have different charges, one positive, one negative, then it's an attracting force. Okay. All right. So, for if we had here instead of a mass, if we had a charge right there, well, then another charged particle, and let's say an opposite sign charged particle, would be an attractive field, so it would look like this. Depending on where you are, different forces. You're further away, shorter. If you're in a different location, then a different direction. The picture's going to actually look an awful lot like this. Okay. All right, so that also is a force field. That's what you would call an electric field. Again, no surprises. Quick pause. How are we doing? Everybody on board? Okay. All righty. Now, I want to move on now to a completely different physical scenario. I don't want to represent forces anymore. I want to represent a completely different thing. This is what I'm going to call a flow field. And the idea is, let's imagine a fluid where there is a flow of the fluid. For example, in this room, I'm not sure if there's any air conditioning running. I feel like maybe I hear something. Anyway, let's suppose the air conditioning is coming out over there. Well, that's shooting air out of the wall, and the air is then flowing maybe this way, and there's a movement of air up there over in that direction. And then it gets to that far wall, and it can't go any further, so it's got to kind of bounce off, and there's probably some movement of air of some sort everywhere in this room. Well, that's a very complicated thing. How is the air moving in this room depending on where you are? One way to represent it, I'll observe, is that if you can tell me for every point, so here's a point right there, right? If at every point, if you can tell me what the velocity of the air is at that point, that is a complete description of how air is flowing, right? If you know velocity, that's a function of, velocity is a function of location. And notice what that means is for every point, we need an associated vector. Structurally, mathematically, it's the same object that we just got through talking about. For every point, there's an associated vector. We're just visualizing a different physical sort of example of it. Instead of representing forces, as we were here, we now want these arrows to represent velocities. And here's an example. You may have, let's say here's a city street, and there's a little bit of flooding in the street, and the water's flowing along the street. It's not just sitting there, it's flowing along. And maybe the water is flowing a little faster in the middle of the street. Maybe it's flowing a little slower, sort of over at the edge by the curb. Which again, I think is somewhat physical. Then this kind of a picture represents that, right? You can see that at points here in the middle of the street, you have a faster flow, longer velocity vector. And at points over here near the edge, you have smaller velocity vectors representing slower movement. How are we doing? Is everybody on board with the... Okay. Now, notice, very importantly, this is not representing forces. Right? So, students have a unfortunate tendency to think of one physical metaphor that they want to decide that they're going to hang their hat on and stick with it. And I don't need to visualize flows of fluids. I'm just going to always think of everything represents forces. Or possibly the other way around. Possibly students will say, well, look, this fluid flow appeals to me. I totally get that. I don't know what he's talking about, a gravitational field, electric field. This is all highly unrelatable. And so I'm going to think of this in terms of flowing of fluids. And both of these strategies are bad ones. You do need to understand both of these. I'm going to call them physical metaphors for vector fields. They're very physically different, and they serve very different roles in understanding vector fields. In some ways, some of the applications that we're going to do, some of the mathematical objects that we're going to define, you really, really have to think about it in terms of forces. And it doesn't really make it makes a different kind of sense, but it's a lot harder to make sense out of if you think in terms of fluid flow. And some of the math that we're going to talk about really makes a lot of sense if you think about it in terms of fluid flows, but not so great if you think of vector fields as representing forces. So it's important to understand both of these, like I say, both of these physical metaphors, and furthermore to make sure that you see the distinction between a picture representing how fluids are flowing versus a picture representing how forces are distributed. Okay. All right, here's another, I'm going to call this a fluid flow example as well. And you might imagine that here we're looking down into a bucket and someone stirred the fluid in this bucket, and that would create a fluid flow. Yeah, something like this. Okay. All righty. Okay, so here's another kind of a vector field. We've actually seen this one before. You can probably see this coming. You see where it says gradient right there. We didn't think of these as vector fields at the time, but here's what we did do. If you give me a real valued function, here, let me zoom. Real valued function. Output values are real numbers, right? We've talked about how at any given point you can compute this thing called the gradient, which of course is a vector. Now, at the time, we were picking and sticking with a single point, right? It's only at this is the point where we are, and I'm not really interested in what's happening over here. Okay, so we pick a single point, and we only really thought about gradients at one point. But I observe, the innocent observation, that, well, in fact, this, you give me any point in the domain, I could compute the corresponding gradient vector at that point. So for every point in space, gradients of real valued functions give you corresponding vectors at those points. In fact, gradients are vector fields. For example, look at that function right there. Familiar? I think we may have studied this exact function. Real value, function of two variables, x and y. There's our formula. The gradient we know how to compute, and here it is. Right? A couple of partial derivatives, no big deal. Here is in chapter 3 where we would just plug in values of x and y, never to be reconsidered, right? And we would think of the gradient as being, a couple of numbers, 6, 8, something like that. Thinking of how that gradient looks only at a single point. But let's just not. And notice that what that means is that for every point x, y, I now have a resulting vector 2x, 2y And this works for no matter what point you pick. Right? If you pick that point or that point or that point, well, for each of these points, there is a corresponding, compute for the formula. And you get therefore a vector field. At every point, there's a vector. Everybody on board? Okay. All right. One little quick bit of foreshadowing. Why am I mentioning gradient fields here? There's two reasons. One is I'm trying to give you examples of vector fields, and this is something that's familiar-ish, right? And so it makes for an easy example for me to point out. There is another reason, and that is that it turns out that in a very powerful and sophisticated way, gradient fields are special. There is something unique about them. And I cannot tell you right now what that is. We don't have the tools developed yet, but we will pretty soon. It's either later this week or early next week. Yeah. Okay. So anyway, a little foreshadowing. Okay. So all of that's been building up to this definition. A vector field on Rn is just a function from Rn to Rn. That seems like a weird way to say for every point there's an associated vector, but you think about it, that's kind of what this is saying. For every point, for every point in my domain, this function is just telling me how to go about finding the value of the associated vector. Okay. All right. And so a real quick picture, right? So you give me a point in R2, right? Take that point in R2, plug it into your formula, capital F, whatever your vector field's name is, plug in, and out comes a vector in R2 that I think of as being the vector associated to that point. So this output, you can call this the output vector. Sometimes you might also call this the field vector. This is the vector that the vector field, namely this function, associates to the original point. Okay, so everybody see how then, this takes a little bit of you gotta think it through, but in fact, if you have a function from R2 to R2, you could interpret that function from R2 to R2 as giving you a vector field. Now, I do want to point out, just to avoid, to recognize the potential confusion and hopefully reduce it, that there is a different way to think of a function from R2 to R2, right? You could think of a function from R2 to R2 as well. The input, the domain is some little world over here, and the output, is some little world over here. And for example, you might think of such a function as a change of variables function. In fact, we've done a fair amount of this already. We've seen a bunch of formulas giving functions from R2 to R2, and we've been using them to do change of variables. So I'm not saying that all functions from R2 to R2 have to be thought of as vector fields. Not at all. I'm just saying that if you have a vector field, you can think of it as a function from R2 to R2. And side note, yes, there are other uses for such functions. Okay, so again, think it through appropriately to the circumstance. Okay. All right, so let's see some examples. Here is a function from R2 to R2. You'll notice two variables go in, two values come out. So R2 to R2. I want to think of this as a vector field. Wow, that's a change of variables function. Let's think of this as a vector field. And what is this? What's this field look like? Right, how do you I'm going to say plot these? By the way, be careful. There's a temptation to say, how do you graph the vector field? Very importantly, that's not what we're doing. We're not looking at graphs. Graph would be some sort of thing in R4 with two input variables, two output variables, a grand total of 4 variables. We're not graphing here. Right? This picture that we're about to draw, not a graph. This is just a picture that in yet another way allows us to get some geometric sense of what this formula says. Okay, this is reviewing it as a vector field. Okay, notice the field vector, no matter where you are, for any x and y, who cares where you are, you always get the same field vector. 2, 1, right? So you're here at this point, field vector is 2, 1. What about over at this point? Field vector is 2, 1. Yeah? How about over here? 2, 1. Always 2, 1. Same output vector, same field vector for every input point. Everybody on board? Okay. All right. Here's another one. Now this is different. F of xy is equal to xy. Now there's a temptation to call this, hey, this is wow, what a simple vector field. This function takes x, y, and it kind of doesn't do anything to it. There's a temptation to look at this and think, oh, well, then this is a picture of some sort of singularly convenient vector field, because after all, nothing happened, right? So that has a certain kind of a look if you're looking at a graph of such a function. Maybe a different sort of a look if you're looking at a level set of a function. We're not doing either of those things, so try not to piggyback on such points of view. This is a completely different setting. For every point, our field vector being that position vector, it gives me a different picture. It's not unlike another picture we already drew, but for every point, we look at the position vector, and that is our field vector. So likewise, here, for that point, the position vector is my field vector. For a point way over here, the position vector is the field vector. Right, so you get one of these you get a radially outward looking vector field. And I mean, unexpected, right? That this picture that we're looking at here, you kind of feel like, yeah, but there's kind of a roundness to this. Because there's a roundness, shouldn't there be like trig, or at least a square root in the formula for this vector field? But there isn't, right? It's just this. Is everybody happy? Okay. So yeah, I gotta, see a certain number of examples and kind of, play with vector fields to get a sense of how the formula associates to the resulting picture. Okay. All right, here's another example. Let's think about this one here. So for every input point x, y, my field vector is negative y, x. And that, again, seems like it ought to be pretty simple. And I guess in a way it kind of is. Different points of view you can take on how to plot, how to draw a picture of this vector field. One is you could just plot a bunch of points. Just pick a bunch of x, y's, compute the negative y, x, and draw them on the page. Right? There is a nice trick to observe here, and that is notice that for every point x, y, the field vector negative y, x has the same magnitude. You can see it right here. The input point, magnitude, square root of x squared plus y squared. The field vector, magnitude, is square root of x squared plus y squared. After you square out that minus sign, move the terms around a little bit. So that's an interesting thing. And furthermore, notice also they are perpendicular. So that tells you a tremendous amount of geometric information for this peculiar little example here. The field vectors and the position vectors for the related point They're always of the same magnitude and perpendicular. And that suggests a picture like this. So for any point, you think about the position vector for that point. The field vector is perpendicular but of the same magnitude. Right, and likewise, say over here, there's the position vector, the field vector, perpendicular, same magnitude. And so, as it turns out, then this is a vector field that seems to look like sort of a stirred pot, counterclockwise here instead of clockwise. But kind of looks like a stirred pot. Everybody okay? All right. Okay. Oh, by the way, there is, you'll notice, another possibility based on observing simply the orthogonality and the length coincidence that happens with this vector field. How did I know from looking at this and merely these two observations, how did I know that the pot was stirred counterclockwise? Couldn't it have also been that for that point, field vector perpendicular of same magnitude, couldn't it have been like that? How did I know it wasn't this? In which case, again, the pot would have been stirred clockwise. And this is just a matter of plugging a point. You just notice, right? So it's easy to plug in, for example, the point 1, 0. You plug in 1, 0 and you get 0, 1, not 0, -1. Cool. All right. Okay, this is a pretty good stopping point. Yeah, look at that. It really is a good stopping point. Okay, so we will pick up here at let's say 11:15. See y'all in 12 minutes.